Hello everyone, welcome back to our channel. Today is chemistry day again. Okay, we'll talk about covalent bond number 2. Okay, we have number 3 next week. Okay, previously number 1. Okay, let's move on. Okay, so today we talk about a giant covalent structure. More than lots of atoms are joined together by covalent bonds as a bag structure. We call it giant covalent structure. In some literature, they also call it as a covalent network structure. They're the same, identical. It's a bag structure. Many atoms are connected by a covalent bonds together. So, for example, carbon and silicon, they can form 4 covalent bonds with each other. Right? So it is a good candidate for them to form a giant covalent structure. We'll discuss them one by one. Some similarity but some differences between them. So it's a bag structure, so it is not solvable. So it's hard to break. So high melting point and high volume. So just remember it is big. And then a covalent structure is a very big. Okay, can move around. So very low electrical conductivity. Okay, so you can look at this table. You can look at the giant covalent structure and all are nothing. But the polar one, okay, they can conduct electricity in the molten state. Oh, we first start with silicon. Okay, silicon covalent and network structure. First of all, silicon can form a 4 covalent bond with each other by themselves. So they can have what's called tetrahedric structure. Tetrahedric structure, continue tetrahedric structure. Okay, so it's a big tetrahedric structure. So you have to remember symmetric, so 109.5 degree. Okay, the magic number, the most separated one. Okay, and you can draw this structure in 2D way too. Okay, silicon 4 together 4 again. Okay, and this is another variation. We call it silicon oxide. Silicon oxide is just very simple. Just add an oxygen atom to each silicon bond. Yeah, so silicon bond and an O here. Oh, and it becomes silicon oxide structure. Still tetrahedral. Tetrahedral because silicon is a straight line bond, okay? So you can see the thing also it's still 109.5 degrees degree, okay? Still a tetrahedral structure. And you can see one oxygen is bonded to 2 silicon, right? Yeah, 1 to 2. So you can see the ratio of oxygen to silicon is 1.2. Yeah, 1 oxygen bond to 2 silicon. Okay, so ratio is like this. Okay, so funny thing. Okay. So you can see it is a giant structure, so they are solid state in room temperature, but carbon dioxide is a gas state in room temperature. And we move to carbon. Carbon has more variation in the giant covalent structure, more funny way. So they have different structure A, B, C, D. 4 structure also made by carbon by itself, so we call it allotrope. Allotrope is a concept that they can be formed by the same element, carbon, but with completely different structure. Okay, diamond, graphite, graphene, carbon nanotube, filament, all are allotropes of carbon, only carbon. Okay, the first one is similar to silicon, tetrahedric structure, and this is the famous, everyone love it, diamond structure. Very strong structure. Okay, 109.5 degree tetrahedric structure, exactly the same as the silicon one. Exactly the same, okay? But it has no free electron, so low conductivity for this one. And high melting point, high boiling point, everything is the same as silicon. Next one is the graphite. Graphite is a layers of carbon, but this time one carbon is bonded with 3 carbon only. So it has 1 free electron move around within the layer, so this free electron can conduct electricity, okay? So within the layer there's 3 electrons, but the 3 electron can't move around. Can't move between layers. So layers and layers of this kind of structure, 1 carbon bond to 3 carbon, and we call it graphite. Graphite is daily life because they have different layers, and layers are bonded by a weak van der Waals mid-London force only. Okay, they are not polarized, so they are slippery. They are soft also. They are used as pencil. It's the graphite structure. And later on, people think about, oh, can we make it as stronger? Yes, we try to make the graphite layers, join them together as a big one layer, and we call it graphene. Graphene is exactly the same structure as graphite, but 1 layer. If we break graphene into different layers, and they go back to graphite. Okay, graphene. So graphene has the same property, conducting electron, can conduct electron. So we just 3 electron move around. And later on, they don't think about it's too bulky, right? Graphene is a big layer, so we time to roll it up. Join the 2 opposite sides together, roll up a graphene and become a very famous nanotube. Okay, Same structure, very strong structure. So we call it a strong tensile strength, a strong physical force strength, okay? And good conductivity too, but not that bulky, okay? It can be smaller, so we call it nylon too. And at the same time, people think about, whether they can copy soccer structure, making carbonated dots in the socket, making a socket structure of carbon, and we make it, okay, we call it filament. Filament is actually is a socket shape, okay? And they are also joined together by they are non-polar, they are connected together between filament is weak van der Waals with London force. So you can see all these things is 4 carbon, 3 carbon, and we later on we'll learn about it. It's 4 carbon, so it's sp3 hybridization, 3 carbon is sp2 hybridization, and the shape diamond is falling silicon tetrahedral, and the other is just 1 to 3, so it's a trigonal plane. Okay, 2D structure, but we roll it up so become an anon 2 filament. Okay. And next we talk about ionic and carbon bond. We compare them. We learn a lot about them, but we want to compare them. First of all, covalent network structure. All the bond is a covalent bond. Okay. And between molecule there is no bond. Okay, they are neutral by themselves. But for a lot of ions, okay, maybe within themselves they have some covalently bonded thing. It becomes a big ion, okay, and the ion has ionic bond. So for ionic bonds, sometimes they are mixture between the covalent bond within the molecule, and between molecule is ionic. So within and between, okay. And next we talk about in details what is the intermolecular force. We want to talk about in details about dipole attraction. We want to separate between the temporary dipole and the induced dipole, permanent dipole, and whatever. All these dipole forces, we call it London force, except for the hydrogen one. So intermediate force include London force, dipole, induced dipole, and hydrogen force. All these things we call it intermolecular force. Okay? And we said van der Waals forces, it's different. We don't want to we want to separate the strong hydrogen bond and the other weak one. So we call the 3 weak one as van der Waals force. So all van der Waals force and hydrogen bonds are this kind of bond. Okay, polarized bond. Okay, but we want to say that the van der Waals bond is the weaker one. The London force, the dipole, induced dipole, and dipole one, and the strong one is a hydrogen bond. So van der Waals bond is different from hydrogen bond. You have to bear in mind. Okay. For example, when a dipole will move close to a non-dipole, you will make the non-dipole induced dipole, right? Attract the will repel the electron out. Okay, so they will have a dipole induced dipole force. Okay, they must be attractive. Okay, but when two a non-dipole thing has a randomly moving, they certainly change. Okay, and they also can have a temporary dipole, okay, attraction. Okay, but this one is weaker because both are temporary. Okay, so you should distinguish between polar, induced polar, and temporary polar and induced polar dipole. Separate between them. Okay? The lower one is the weakest, and we call it London force. London force is random one. Everything has London force. You can say, yeah. Everything has London force. But for the upper one, one of them has to be a polar molecule. And the other is even stronger. They are themselves a dipole already. They are dipole, and two dipole as force to each other. Of course, they can be attractive or repulsive. Of course, they will flip. Okay, such that they are always attractive. Okay, so it's just dipole interaction. Also, although we can have a chance that they will have a dipole repulsion, but they always will reorient quickly. So always can be assumed they are attractive for the dipole. So remember, dipole is strongest. Okay. And then the dipole, induced dipole, and then the random dipole, temporary dipole, and induced dipole. So one by one. And amongst these dipole attraction, we have some of them are exceptionally strong. We need to give it another names, okay? And we call it hydrogen bonding. Hydrogen bonding is the strong dipole attraction. We give it a special name. There's only three by definition. It's really definition because they are extremely strong. Okay, NH, OH, and FH. Okay, just these three we call it hydrogen bond, not other H. Okay, NH, OH, and FH. You need to remember them. Yes, it's definition because they are exceptionally different from the other dipole attraction. The gap is too big, so we need to remember NH, OH, and FH. It is a fact. Okay, so you need to remember it and you can recognize it. Okay, somewhere. and we call it hydrogen bond. And a chemical formula, sometimes they have OH or HF, but doesn't mean that they have a hydrogen bond, because they maybe the C's OH are not bonded. Actually, the HF are not bonded. But in the chemical structure, in the formula, you can see, you need to really draw the structure out, and then you realize whether the O and H and the F and H and the NH, whether they are bonded or not. If they are bonded, hydrogen bond, strong one. Okay? And when the last one, you have to make sure what you mean that not hydrogen bond. Exceptional strong one, you take it out, and the remaining we call it van der Waals force. Okay, so the strength trend is very clear. Is the melting point channel. The stronger the bond, the higher the melting point. Yes, of course. So van der Waals force is weaker than hydrogen bond, so the strength is weaker. The melting point is lower for van der Waals force. Although a London force is weakest, okay, if there is no other intermolecular force, then it is still the strongest intermolecular. So among that molecule, is the essential one. It is the most prominent one, maybe. So be careful. Weak, but can be the most important one for that molecule if it's the only force between them. Okay. And this is some atypical molecules with hydrogen bond appearing in IBDP. You to remember them. Okay. Chloric acid HOCl, ethanediolic acid HOC 0H. Okay. Ethan 1,2 diol, and then urea H2N0. Okay. So you have to remember when you have some mindset that this 4 you will encounter frequently in IBDP. Okay. And you also know the trend, because why we said that HO, HF, and then H are so strong, because you see the trend down the trend. You can see down the period. Completely different about the melting, exceptionally high for H2O, HF, and NH3 compared with the others. Okay. So we said that the hydrogen bond is significant and prominent. Okay. And the other just have London force. And you know the London force is a random force, right? So the more electron, the higher the London force. So the melting point rises up a little bit later, because they have more electron. And the physical property of covalent subject, volatility and electrical conductivity. Volatility is the opposite of a melting point. Right? If a melting point is low, volatility will be high. Got the point? Okay. So it's just the same concept. London force is weaker than dipole. Dipole is weaker than hydrogen bond. So melting point is London force is lower, higher. And volatility is opposite. London force is higher volatility, and then dipole, and then hydrogen bond. Opposite. Just remember the concept. Okay. Solubility is making hydrogen bond with water. Maybe the molecule itself has hydrogen bond structure, HN, HOH, or HCl, or maybe they have the oxygen structure. They have a lone pair, and then they can form a hydrogen bond with the hydrogen in the water. Right? So be careful that this one can be soluble too. Look for lone pair oxygen. Okay. And chromatography is a concept how we can separate mixture of a compound. It is a concept that we have two things. Okay, one stationary phase and one is a mobile phase. One thing does not move and one thing move. Okay, and we want to separate the mixture because they have different affinity to the thing that doesn't move and the thing that's moving. And for example, paper chromatography, paper is the stationary phase and the solvent is the moving phase. See whether the thing is more sticky or affinity to the solvent or to the paper, and then they move with the solvent more and move with the solvent less. And this is a measurement, we call it a retardation factor. If they move with the solvent more, so they will move higher or lower. So we have the retardation factor 1 and 0. If the retardation is 0, it means that they don't move. Okay. Their affinity to the fixed stationary phase is 2 great. Okay. If this is 1, they are not affinity to the stationary phase completely. They move around. Okay. So RF equals 0 is at the bottom. RF equals 1 is at the top. Okay. Make it simple. Okay. And a covalent bond, we call it a resonance structure. When one connected A connected to B with one single bond and one double bond, okay, they have resonance structure because look at here. How can the two structures identical? Right? So actually they happens randomly. Okay, sometimes to left, sometimes to right. Actually, this bond will be delocalized. Then the bond will be 1.5 for both. Very funny. We call it resonance structures, and we'll draw a broken line. Sometimes not. Okay, we'll tell you the rules. Okay. For example, all this thing we have a banded shape. All the thing with a banded shape, we'll draw the broken line. Okay. And be careful, it is double bond, single bond is here. The band shape is here. Band bond is here. So we look at the Lewis structure, very complicated, but it is required in IBDP for you to draw this Lewis structure. Remember, Lewis structure was the key bond. Okay? Alternate dot and cross dot dot. Okay, dot cross dot dot. Okay, cross dot cross dot cross dot. So very be careful about the cross and the dot. Alternate atom, alternate dot and cross. Okay. And but the two exceptions that we don't draw the broken line. Okay. For example, if it is a linear structure, okay, we don't draw the broken line. Okay. If it is a three-bond resonance system, okay, three possibility, we don't draw the broken line too. So be careful. When do you draw the broken line? Okay. And a typical example is a benzene. Okay. Wow, alternate single and double bond, and also draw the broken line. This drawing a broken line is experimental result. Okay. All the bond inside is all 1.5 covalent bonds property. Okay. We are not drawing it out by imagination. This is a experimental result. Okay. Compared with this C6H12. Okay. All a single bond, no resonance structure. Okay. Thank you for going through with me. We learned a lot of new things today. And it is essential, especially when we learn about organic chemistry and some reaction. Okay, we need this concept. Okay, so if you like our sharing, remember subscribe and share with your friends. Okay, see you for next. Bye bye.